My presentation?
Yes, we can see your screen. You can start. Thanks.
Okay, thank you. So hello everyone, and thank you so much for inviting me to give this talk today. And also thanks to Neil for introducing a lot of the concepts I'll be going over. So apologies if there's any repetition, but there's also going to be a lot of new stuff, so bear with me. So I'm going to focus a lot on investigations with the LIGO and Virgo detectors regarding gravitational wave background mapping. But I'll also, towards the end, tell you about some prospects that we've discovered for the LISA detector. So let's start off by discussing what gravitational wave backgrounds are. So we consider gravitational wave backgrounds to be an incoherent superposition of all of those gravitational waves we do not directly resolve with our detectors. And typically, because they build up in this sort of confusion noise, as Neil also mentioned, we typically treat them with stochastic variables. So we consider these to be stochastic backgrounds. So gravitational wave background searches set out to estimate the monopole of the gravitational wave background intensity, and also perhaps map the intensity on the sky. So I'll be focusing on the latter today. Now, gravitational waves have a variety of different origins, so do gravitational wave backgrounds. So the first distinction is typically made based on redshift. So smaller redshift gravitational wave backgrounds are considered to be astrophysical from astrophysical sources such as CBCs. And beyond that, we do also consider cosmological sources. So these can be anything from gravitational waves from inflation, or something a bit more exotic like cosmic string networks or phase transitions and so on. So because I'll be talking about LISA and LIGO, let me just brush off what the expected stochastic backgrounds could be in these in the relative bands. So in the LISA band, first and foremost, we always think of galactic white dwarf binaries. They will be a very loud signal. A lot of them will be directly resolved, but then a whole lot more will build up to form this confusion noise that we would like to analyze and subtract. Beyond that, we expect to have some form of stochastic signal from extragalactic stellar mass binaries. So these are the binaries that then go and merge in the LIGO band, but they're still in spiraling in the LISA band. And beyond that, still we hope to have some primordial background to constrain. In the LIGO, or ground-based, I should say, detector band, the main stochastic signal that we are hoping to detect is made up of shot noise from the binary black hole and neutron star signals that we do not directly resolve and match filter out. So you can think of this as some sort of popcorning-like signal that populates the time stream very sparsely, but they're all sort of sub-threshold signals that build up. And so hopefully by integrating over a lot of data, we can finally be able to measure that as a single signal for the background. And beyond that, again, hopefully maybe with 3G detectors, we might be able to start seeing some primordial backgrounds. So all of these different gravitational wave signals have different spectral dependencies, and that's something that we can use to differentiate between them. So here is a very classic plot where you can see how different gravitational wave signals populate the frequency space, and how we have a variety of different projects to go and test, either present or future, to go and test these signals. And on the y-axis here, I'm plotting the omega parameter for gravitational waves, specifically because when we're thinking about stochastic backgrounds, we like to bring it back to cosmology. So omega, just as any other cosmological energy content in the universe. And the omega parameter, as you can see from equation 1, is directly related to the intensity of the gravitational wave background. So even though with the data, we actually go and measure or constrain the intensity of the background, we always have in the back of our minds that this is directly related to the energy content, overall energy content of the universe. And I'm gonna go one step further and say that we typically assume the spectral shape of this omega parameter to behave as a simple power law. This is a simplification, so we can do better if we have slightly more sophisticated models. But for many stochastic searches, we do make the simplification as we do a lot of broadband integration to simplify our searches. So for the most part, I'm going to assume that the omega parameter for gravitational waves just behaves as f to the alpha, where alpha is my spectral index. And depending on what spectral index I choose, I might be talking about a different background. And because we're going to be talking about mapping, let me also introduce what anisotropies we expect gravitational wave backgrounds to have. So in fact, most of the time we expect our backgrounds to be statistically isotropic. So for the most part, we assume we can fully describe the anisotropies of the signals we're searching for to be described by their angular power spectrum CL. And there are several estimates for what the CL should be for both astrophysical and cosmological backgrounds. Here I'm reporting on some searches for astrophysical backgrounds from Cousin et al. And Jenkins et al. And as you can see, there's a bit of tension in the literature as well. So as soon as we will have a positive detection of these, we'll be able to figure out exactly what's going on out there. So now I'm going to start the sort of more painful part of the talk. I'm going to get this done at the beginning. And so hopefully it's going to be nice and quick. So bear with me for the next few slides. I'm going to talk to you about the maximum likelihood map making methods. So stochastic searches typically just start from a Gaussian assumption. We saw this also in the previous talk. So we just write down a Gaussian likelihood for the data, where the data is considered to be made up of a pure signal component and a pure noise component. And they're both assumed to be behaving like Gaussian variables. Another key feature in this likelihood is the full data covariance. So a lot of importance is tied in with how we treat the data covariance and how can we approximate it and model it. And you can see that it is made up of a component, a pure signal component, which contains the intensity I of the gravitational wave background, which we're trying to measure, filtered by some detector dependent function A, which knows everything about how the detector is sensitive to the intensity, and the noise covariance N, which we either hope we can model perfectly, or we can try to iteratively estimate. So all the mapping that we do boils down to just maximizing this likelihood and drawing out the optimal map estimate. Now with LIGO, we can also make a further assumption that the noise fully dominates the measurement at any given time. So we do not really need to use or estimate the full data covariance. We can actually just use the noise covariance in its place. And furthermore, you know, being noise dominated is actually a big problem. So to beat down the noise, we actually cross correlate between different detectors. We never use the autocorrelated data from a single detector. We always need detector pairs to do stochastic searches. And so what we hope this leads to is that by averaging over a lot of data, so noise averaging or time averaging our data, if we take the cross correlation between two different detectors, eventually the noise correlations just drop out. Should be no noise correlations between two detectors, you know, far apart on Earth, and we're left with a pure signal component which contains information about our background intensity. And so what we do is we actually just write out the likelihood and the residuals of the cross correlated data and draw out this mapping solution, which you see here in equation 5. I realize there's lots of equations here. All I really want to underline is that our intensity on the sky, so n hat is here, a direction on the sky, is obtained after a Fisher matrix inversion. So this Fisher matrix F curly F contains all the information about how different directions are correlated through our detector sampling of the sky. So the gamma function that features here is the detector sky response, and the way that the responses of the two detectors correlate tells us how we're going to sample the intensity as a function of direction. And this Fisher matrix inversion can be very, very tricky because it is a highly non-diagonal matrix, at least in general. So a lot of work is put into figuring out how to regularize this matrix. So for LISA, the story is slightly different because here, first of all, we cannot just assume that the noise dominates the measurement. So we do need to use the full data covariance and use an iterative estimator to draw out the intensity on the sky. And luckily for us, LISA does have multiple data channels. So what we can do is we can write the full likelihood that contains all the information from all the data channels and just treat the data vector from all the channels to be our Gaussian variable. And that leaves us with this big mapping solution. I realize they're getting bigger. But again, all I want to underline here is that So first of all, this is an iterative solution. So we use first estimate for what we think the data covariance should be. And we let the algorithm iterate over all the data to draw out the map, optimally fitting map I tilde. And again, we have a big Fisher matrix here, which contains all the information about how different directions are correlated by our detectors. And again, this is going to be a very singular matrix, and it's going to be tricky to invert this matrix. Now, at this stage, we have our mapping solutions, and to actually put them into practice computationally and feed in the data, we need to make decisions about how we're going to discretize space. So one of the most intuitive ways of discretizing space can be just pixelizing the sky. So you can divide up the sky into equal area patches and try to estimate what the power of gravitational wave background is in each patch. An equivalent way is using conjugate space, so spherical harmonic space. And you can see that as I expand the sky in LMs and I go up in L max, I can recover a similar resolution with LMs that I have with the pixels. So there's a direct relation between the number of pixels that I'm using on the sky on one hand and the L max that I'm expanding to in the other. And these are complete descriptions of the sphere. So you would think that they'd be entirely equivalent to use when making maps. And in fact, they're not. This is because we do need to make decisions regarding how many pixels we're using or what Lmax we're expanding to. And this creates different issues for the different sets of coordinates. So in fact, in practice, most of the time, we make this decision based on what specific signals we're interested in measuring. So typically, spherical harmonic searches target very extended sources on the sky. So some big correlated patch of power on the sky that we're trying to measure. And they're also somewhat well suited or better suited for statistically isotropic backgrounds, just because all we're really interested in that case is measuring the angular power spectrum CL. And if we're just working already in the native space of the angular power spectrum, so in LM space, this might be a little bit more straightforward and perhaps even a little bit more computationally efficient. So there are some assumptions that we can plug in LM space that can make things a little bit easier. Conversely, we do use pixel space, especially when thinking of point-like sources. So you might have a sky full of very uncorrelated point sources. And in this case, you can consider each pixel to be completely independent. And so this is basically what we call the radiometer search in LIGO. You can use just the diagonal of your Fisher matrix and treat all the sky as just being completely independent. And you can take it a step further and target specific directions where you think there should be a signal. So say, for example, the galactic center or some radio source. So you cannot quite orient a gravitational wave detectors, but there's something that you can do in post-processing to sort of zero in into certain directions maximally and try to draw out some signal that you think is coming from a specific direction. So now I'm going to talk to you about the recent results we've put out with the LIGO Virgo collaboration on anisotropic stochastic searches. So this is the first time that we use data also from the Virgo detector for this type of search. So it's very exciting. And let me just underline that, again, with stochastic searches, we are always using the cross correlation of data streams. So we can think of our data as actually already being in cross-correlated space. I usually think of it as baseline data. So we have the LIGO baseline that is the LIGO Livingston LIGO Hanford baseline, and then we have two more baselines that include Virgo, so Hanford Virgo and Livingston Virgo. So we now have a network of 3 baselines that are observing the sky. But before I show you the results, let's just brush up very quickly on what the LIGO response functions look like. So because LIGO is made up of Fabry-Perot cavities, we can operate in the low frequency limit. And this simplifies things a great deal, especially if we then compare with what happens with LISA. So the arm transfer function does not depend on frequency. It only contains dependencies on the sky direction. So that's what N hat here is labeling, and the polarizations plus and cross. And when we go and correlate the data streams, what we're interested in is actually the overlap response, the correlated response to the sky from the two detectors. So that's what we're looking at here, which marginalizes over the polarizations, and again, is only a function of direction. But because the Earth is actually moving with respect to the signal, it does have a time modulation. So this is what our response functions on the sky looks like instantaneously. So this overlap response has one hot direction. Intuitively, it's just the perpendicular direction, and then two cold directions, and it's nice and smooth on the sky. But then as the Earth scans round and round, you can see that also the overlap function migrates on the sky. And you can already see, if you kind of integrate by eye, that you're going to get a very uneven sampling of the sky. So it's this uneven sampling that makes our Fisher matrix highly non-diagonal and highly sparse, so very hard to invert. There's going to be some patches of sky that you basically never look at, and the sampling is just going to be all over the place. So deconvolving this response is really the hardest part of our job when map making. So here is our recent paper. It is very recent, as you can see, from the LVC collaboration. So we do not have a detection of either isotropic or anisotropic backgrounds, unfortunately. But this was still a very exciting paper to work on, again, because we've added Virgo to the array. And so there's been a lot of new interesting directions we can take our analyses in. So I'm going to talk to you about the radiometer searches, as I was mentioning before. So both broadband integrated searches and narrowband searches, where we chop up frequency space and try to constrain the gravitational wave background intensity coming from different little bands from specific directions on the sky. So target searches on the sky. And specifically, the target searches look at the X-ray source Scorpius X1, supernovae 1987A, and the Galactic Center. And then finally, I'm also going to show you results from the spherical harmonic decomposition search. So the spherical harmonic decomposition search is, of course, carried out in LM space and is targeting these extended sources. So it's more thinking towards a primordial background, whereas the radiometer search works natively in pixel space. So radiometer searches consider each direction on the sky to be fully independent. So we only use the diagonal of the Fisher matrix when drawing out the optimal map solution. And you can imagine this is really simplifying our problem a great deal, because the whole inversion boils down to then inverting just a diagonal matrix. So the whole issue with inverting a singular matrix just washes out. Whereas in the spherical harmonic decomposition, we do use the full Fisher matrix, and that we run into a series of problems there. So these are the results for the radiometer broadband search. You can see I'm presenting 3 maps. So these maps all correspond to different spectral indices. So I'm assuming, again, that my background that I'm searching for has a certain spectral shape, and I am broadband integrating over that shape. So marginalizing over the frequencies to estimate an optimal overall map of my signal. And here I'm doing it, treating each direction as if it's completely independent. So alpha equals 0 is the alpha that we use typically when we think of a scale invariant omega, a scale invariant background in omega, so something that might behave as a cosmological background, whereas the alpha equals 2/3 is the index we use when thinking of inspiral dominated backgrounds, so something that could be an astrophysical background. And here I'm just reporting the maximum SNR that we see in these SNR maps. And again, these are values that are drawn out using the 3 baselines. So this is different from what we were doing with the previous 2 advanced LIGO data runs, where we're only using the data from the single Hanford-Livingston baseline. So there's a considerable improvement, so between a factor of 3.5, 3.8 in these limits, which is due not only to the fact that we've actually improved the detectors in the meantime. So LIGO, Hanford and Livingston have improved between 102 and then 03, but also because we've added Virgo. So this doesn't quite scale linearly, right? The more detectors we add, the better the better a job we're gonna do with constraining backgrounds. And here instead is the narrowband targeted search. So we're looking here at frequency spectra for different specific directions. So again, imagine that you can zero in a single pixel and try to figure out what is the signal, the stochastic signal coming from that particular pixel on the sky. So that's what we're trying to do here. And we are chopping up frequency space, binning it very, very finely to look for some residual power in any of these specific bins. And this is because we cannot at this stage assume that we do know what the spectral shape of any of these potential sources could be. So we're trying to constrain that as well. And here I'm reporting both the maximum signal to noise ratio we observe for specific bins. So these are the bins relative to the sources that we get the maximum SNR of in that particular direction. But I'm also showing you where we get the most stringent upper limits. So these are obviously different bands. On the one hand, the frequency band where we get the best upper limit is in the sort of more sensitive region of our detector. Whereas the the frequency bin where we get the highest SNR is most often up in the higher end of the frequency range. And that's quite intuitive if you think of this as just being a noise fluctuation, because the noise is just louder in the higher frequencies. And finally, let me show you the results from our spherical harmonic search. So again, these are SNR maps on the sky for different spectral indices that we're weighting our frequencies with. And again, as you can see, there's no detection. Our color bars are well below an SNR of 3. And there is a considerable improvement with respect to the equivalent maps obtained with 01 and 02. Now, as I was mentioning before, the extra challenge that we have with spherical harmonics is the inversion of the full Fisher matrix, non-diagonal Fisher matrix, which we carry out with a singular value decomposition. But there's still a lot of R&D going into understanding what are we doing? Are we doing the right thing? Because there's an arbitrary choice when doing SVD with a non-singular matrix. You are making the choice of what modes you're discarding, and it's very hard to motivate this choice. And there's good news though, because adding Virgo has helped just a little bit in regularizing this matrix, and it only has helped a little because Virgo is that much less sensitive than the LIGO detectors at this time. But as Virgo becomes more and more sensitive, and also as we add more detectors, Kagra or LIGO India to the network, we're going to do a much better job at inverting the Fisher matrix to the point where hopefully at one point we won't even need to regularize it, right? It will just be a regular matrix. And also we're showing the angular power spectrum for the upper limits to the angular power spectrum for the gravitational wave background drawn out from these maps. And just note that the angular power spectrum here for different spectral indices is expanded out to different L maxes. And this is simply because depending on your alpha, your coupling with frequencies on the sky is going to be different. And so you're going to be able to probe different scales depending on what spectral shape you're choosing. So now in the final minutes of my talk, I'm going to talk a little bit about what we've been investigating for map making with LISA. So is there a big difference between mapping with LIGO and mapping with LISA? Yeah, so there are a few considerable differences which make map making with LISA quite challenging compared to the ground. So first of all, as I was mentioning at the beginning, we cannot assume noise to dominate. So we need an iterative solution that takes into account the full covariance of the data. But also the sky scanning strategy and the geometry of the detector are different enough that we need to use a slightly different approach. So let me point out that, you know, the arm to distance ratio with ground-based detectors is very large. So for triangulation purposes, this makes our life a lot easier. Whereas LISA, as a single detector, is this compact constellation that just revolves around the sun. So unless you can use the phase information, you're not making use of the modulation, of the yearly modulation as much as you could. And so you're basically constrained in a very small space to triangulate sources. And also, let me point out that this would be a lot easier if we just had another detector out there observing simultaneously with LISA, but in space it's a lot harder to add a detector. I'm not saying that on Earth it's a lot easier, but once you build a detector on Earth, it's there, whereas with space missions, the story is a little bit different. So of course, mapping would highly benefit from having 2 LISAs, but it still feels like on the Santa Claus list right now. So again, let's look at what the LISA response is on the sky. So with LISA, we do not have Fabry-Perot cavities. We cannot use the low frequency limit. And so not only do we have a time modulation, so we can take a look at what the scanning looks like for the LISA detector in the solar system barycenter frame. So you can see this movie is just showing you how the hot direction just migrates on the 30-degree angle off of the equatorial plane of the solar system constantly. And so, you know, you can see that the symmetry of the scanning strategy is also going to mean that you're not sampling the sky very well, but you know, this is how it is. But so not only do you have this time dependence, you also have a frequency dependence in your sky sampling, which makes our life somewhat easier and somewhat more complicated depending on different aspects. So this is what a snapshot of the LISA response looks like, you know, in the lower end of the frequencies. In the lower end of the frequencies, it's nice and flat and looks like this on the sky. But as you start going up in frequency, you get very interesting modulations. So in particular, notice that we're actually becoming less and less sensitive on the sky, and the sampling is becoming finer and finer. So you somehow open up smaller scales on the sky while also losing information. So it's a balancing act between these two that is going to allow you to make these maps. So what we did was we set out to answer the question, what is the angular resolution that we could potentially obtain with LISA in a sort of best case scenario where you have very high signal to noise ratio signals, and also you've subtracted out all of the resolved signals, so they're not mucking up your reconstruction. And we ran a set of simulations injecting statistically isotropic backgrounds that follow a CL of 1 over square root 2L squared. So that's the gray dashed line here. And we reconstructed these injections, broadband integrating up to different frequencies to see how the sky modulation and frequency modulation of our response function influence the mapping. So what you see is that in the sort of best case scenario of having a loud signal up until an Fmax of 10 to minus 1 hertz, you can reconstruct it up until something like Lmax 15, which to CMB people, this sounds ridiculously low, but it's for us, it sounds great at this stage. But however, it becomes worse and worse as you integrate to lower and lower frequencies. So what this is telling you is that everything's going to depend on where your signal peaks in the frequency domain. So if you're trying to map something that has a very low frequency shape, well, which populates the frequency space in the lower end, even if it's a very, very loud signal, you're still not going to be able to reconstruct it. Thank you. I see, I'm on my last slide. All I just want to say here is that we also did a little investigation to understand, would we be able to map the galactic bulge? And the answer is somewhat. So in the first row, you can see that in a very high SNR case, we can sort of pinpoint the bulge with, you know, some decent resolution. But as soon as we add in the noise, so we do something like a realistic SNR injection, and we take into account the noise of the detector, which competes with the signal, you see that the signal just washes out completely. So not only do we need to worry about where in frequency does the signal peak, we also need to worry about how it interacts with the noise spectrum. And because the noise spectrum ramps up rapidly in the higher frequencies, it makes our life that much harder to have a high resolution with LISA. So I'm just going to sum things up. I've shown you results from the directional searches with LIGO and Virgo, and we're targeting a variety of sources. And as we add more detectors, we're going to become more and more sensitive to anisotropies on the sky. However, precise and reliable map making completely depends on our understanding of how to regularize the Fisher matrix. So there's a lot of R&D in this direction currently. And LISA is a big challenge ahead, but we're not all too optimistic about achieving high sky resolutions with LISA because everything depends on the frequency of the signal. And so the signals we're expecting to have don't really populate that area of frequency space at high SNR. So thank you.
Thanks a lot for the presentation. And I'm sorry if I had to interrupt you during your slide. I was not subtle enough. We have time for questions. So please raise your hand, or if you can't raise your hand, please speak up, because don't hesitate to, if you have questions. Okay, I don't see any specific request for questions. So thanks a lot. I just noted that 2 LISA flying at the same time is nice. That's a good message to send. And thanks everyone for joining this conference. So tomorrow it starts at 9, and I think we're good for the day.